definition of a function. Then we from there we define slope. So the slope, every time you pick 2 points, the slope of the segment connecting those 2 points is y2 minus y1 minus y1, x2 minus x1. Another way to write that is to, instead of writing y, you can just write the function evaluated at this specific point. So notation wise, this would be f of x2 minus f of x1 divided by x2 minus x1. So we then apply this thing over and over again a bunch of different times. And at some point we said, what if I just pick a point at random, and the other point is just gonna be a point kind of some distance from the first point I pick. So the 2 points that we identified, so pick 1 point, we call it x0. So the function at that point was, the y value of that would be f of x0. And then another point, h units away from it. So the next point would be x0 plus h, and the y value at that point would be f of x0 plus h. Yeah? So graphically, if this is my function, whatever it is, if I pick this to be my x0, this would be f of x0. And if I want to be h units away from here, this is going to be h0 plus h, and this is the function evaluated there. Yeah? Does it make sense? So we did that, and the idea was, if I want to know that the slope, not of those 2 distinct points, but the slope of this function at a point, I would have to make those 2 points, 2 distinct points, very, very close to each other, to the point where they overlap. Meaning that as I shrink this h, the more precise my estimation of the slope of the curve is going to be. So we did this for, trying to remember what I did there. There I did, we calculated the slope of a line, right? Mm-hmm. Where it was trivial, we just went through the process. We know what the answer was gonna be. It was gonna be the coefficient of the, of x. And so we just practiced with that process. Didn't really reveal anything, informative. So now we need to extend that, and let's try to find the slope at any point along a function. So instead of evaluating that at a specific point, we want to evaluate it at any random point. Essentially, in doing that, we will end up with a formula that computes the slope at any point of your choice. Okay? So we need to come up with that formula. Let's see how that can be done. So let's suppose that f of x is this. Okay? So I want to know what is the slope of any point and its immediate neighbor evaluating this function. So how can I do it? Well, pick a point to call it z, and then pick the one adjacent to it. So those are x values. So in the graph, this is a parabola. So who looks at these? This could be my point z, and right next to it, there is that z plus h. Okay, but z could be here, and z plus h could be to the left of it. Who knows? That's why I'm just leaving it as a letter and not as a number. So to find the slope, I have to use this idea: the function evaluated at z, the function evaluated at z plus h. So f of z minus f of z plus h divided by z minus z plus h. Yeah? So let's evaluate this thing. And it's convenient to switch things around so I don't have to deal with negatives. So if I put this in here, so I'm flipping this around to avoid the negatives, okay? So I've just changed the order. So then this becomes z plus h minus z. You agree with that? So this is the x coordinate. This is the x coordinate at the other point. This is my y coordinate. F of z right here. So in this case would be just z squared. And this would be z plus h squared. Yep. So let's do some algebra. If you square this thing, you get the first term squared plus twice the first times the second plus the last one squared minus the square. So this is the first part, and this is the second part. Do you agree with that? And then here you have z plus h. Subtract z, you just have h. So here, this guy and this guy cancel each other out. So you're left with 2zh plus h squared divided by h. What else can we do?
Divide everything by 8.
So you can factor out h is common to both terms. So I'm going to go here, so I'm going backwards, sorry. If you factor everything out, you have h times 2z plus h, then divided by h. And after you can factor out, then you can simplify. Yeah? So what does this tell you? The formula for the slope is slope equals 2z plus h, depending what 2 points you pick. The first point is z, and then the h is the point next to it. So if you know how far apart the points are, you know what h is. If you know the point you picked, you know what z is. But what if I pick 2 points that are very, very close to each other? If those points are very close, then h is
0.
very small, right? What is that the width of an interval? What is the smallest width an interval can have?
It can approach
0.
0.
So if you go to the smallest level, let h approach 0, and then you get that the slope. The formula for the slope is 2 times z. Do you agree with that? So you can verify this with numbers. Pick 2 points. Point 3 and h equal to 0.01. And so if you do it the long way, x is 3 or z is 3. So f of 3 would be what, 3 squared, which is 9. Then you pick the next point. 3.001. F of 3.001 is 3.001 squared. And what do you get? Come on, get your calculators out, quick.
Okay, there we go. 9.006.
9.006, do you agree with that? Yeah? So by picking numbers and computing the slope the traditional way, you do 9.006 minus 9 divided by 3.001 minus 3. And what do you get?
6.
6 even, right?
And that was 2 times 3.
So let's see if we can get the same answer using this approximation, using the formula. The formula says that the slope is 2z plus h. Yeah, that's the one we derived up there. So without going through this process, we can figure it out, evaluate these for z 3 and h 0.001, and what do you get? You get 2 times 3 plus 0.001. Yeah. So this shows you that by using just terms or variables, we can end up with an equation for the slope that can be applied for any point on the x-axis and the next point that is h units away from that point that you picked. If you were to do that, the slope that you would be obtaining is given by this. This is a shortcut. So the specific thing that I did here was by picking a point and a point that is 0.001 units away from it. I used the original approach, the slow, lengthy approach, and I got this slope. But then I used the shortcut, and I got a number that is close enough. They're not identical, but close enough. Now, if I pick those 2 points so close to each other that they actually overlap, this becomes 0, and the slope becomes exactly 6. You see that? So, picture doing this I mean, if you had to compute the slope of this curve at some point, which way would be more convenient? To do it step by step, or to just do it like this, end up with a formula, and then just change this value if you need to?
Formula.
But clearly, this is the fastest way. You only do it once for this particular function, and then if you have to calculate the slope in some other location, you would just plug the values in there. You get the same answer. Okay. Remember, this one is only if you're picking 2 points that are overlapping. If you're picking 2 distinct points, the answer will be this. So let's fast forward. What if I get a function that looks like this? How could I do it? But I could do either pick points, 2 distinct points, or do the same thing that I did here. I pick a point z, then a point z plus h, calculate f of z, calculate f of z plus h. But now the algebra gets more convoluted, right? Because you have a coefficient in front, you're subtracting numbers, it's just getting more complex. But the process is the exact same. So mathematicians realized that this was not a very convenient way of doing things, and they said, how about we give a name to going through this process for curves, for functions. So they came up with the concept of derivative. Taking a derivative of a function essentially is equivalent to coming up with the equation of the slope along that function at any point. So essentially, this 2z is the derivative of this function right here. Okay. So the derivative is the equation so the derivative of, say, f of x is the equation of the slope along f of x. The way you calculate this derivative, at least initially, is taking a point, and again with the point we called it z, and the adjacent one. Which we called z plus h units away from it. Then compute, evaluate the function at z, and evaluate the function at z plus h, just like we did there. Once you have those 4 points, 4 values, z plus h, f of z, and f of z plus h, then compute the slope. So it's f of z plus h minus f of z divided by z plus h minus z. This will always boil down to these. We always be like that. And then the next step is make those 2 points, z and z plus h, be overlapping. So in other words, take the limit of this thing. So calculate these. Once you have calculated these things, simplify it as much as possible, replace 0 for h, and see what happens. So you can do this for a bunch of different functions, and it turns out that every time you will calculate that for a parabola, you'll always get the same answer. Every time you calculate that for the cosine function, you will always get the same answer, and so forth. So they realized that we don't need to go through this process every time. All we need to do is memorize a function and what its derivative is, and then if you have combinations of those functions that you can easily compute the slope of those guys just by using those already computed derivatives. So from here they arrived to a set of rules. Rules of derivatives. The first one is the derivative with respect of x of a constant is 0. So this thing right here is the notation for derivative of. Let's see if this makes sense. Derivative is the equation of the slope, right? So if I have a constant, say y equals 3. 3 is the constant. How would this plot in here?
Horizontal.
So this is y. Doesn't matter what x is. Y is always going to be 3. It's horizontal line. What is the slope of horizontal line? 0. So it makes sense. The slope of a horizontal line is 0. You can verify that by going through this process. So this is your function. Pick a value of x, then pick x of h, do all that crap, and you will see that the slope is going to be 0. The other thing that they figured out is the derivative of x to any power is equal to the power, the exponent, times the derivative, n minus 1. Let's see if this kind of works out. Think about this one in here. What is it? 2x, x squared. So this is x to the power, right? If you take the derivative of these, what do you get? According to the rule, the derivative of x to the power is the exponent x and the exponent reduced by 1 unit, 2x. So what do we get when we went through this whole thing? The equation of slope is 2x. Yep. The next property is if you take the derivative of the sum of functions, this is the same as taking the derivative of each function. In other words, if you have a complex polynomial, you're trying to take the derivative of that, you can see that as a sum of individual terms, and you can just take the derivative of each individual term. So it allows you to distribute the differentiation across all those different terms. Then the last one that you need to know is the derivative of a constant times a function is equal to the constant times the derivative of the function. Questions? I'm not proving that this is true. I'm just gonna like vomit it out, it's just the way it is. If you want to kind of prove that this is true, all you need to do is come up with a function, go through this process, and you will see that the answer that you get through this process an hour later is gonna be the same answer that you would get if you applied those shortcuts, okay? But so let's try to figure out how this works. Example. What is the derivative of x to the fourth?
4x to the third.
So slow down. Which property would you use? It's x to some power. So x to some power is this rule right here. So if you use rule number 2, this is the same as it says take the exponent and put it in front of the x. Then write x, and the new exponent is the one from before, reduced by 1 unit. That's it. So it's 4 x cubed. Yep. So how do we get there? I use rule number 2, right? Yep. What about take the derivative of x to the 10 plus x cubed. So how many functions do you have here? You have this guy plus this other guy, right? So when you're dealing with the derivative of multiple functions, what can you do? You can split them up. So that's that. Let's break them. So take the derivative of the first term, derivative of the second term. So now for each term, what do you have? Is the power rule. So I went from here to there by using number 3. And so the next step is power rule twice. So this is, help me out, 10 x to the 10 minus 1. And then for this other guy is 3 times x to the 3 minus 1. 10x to the 9th plus 3x squared. Okay. So if I want to know what is the slope of this guy when x is 1, what is your answer? Well, the slope is, this is the equation of the slope. Put a 1 for x, put a 1 for the other x, and you can calculate. So what is it, 13? Yep. Questions?
Do we need to add h?
No, you only do it, we only did it before we ended up with those rules. So this is if you want to derive these. So this is just an intermediate step. The reason we're doing this is because we said it takes forever. And it turns out that if I change location of this same curve, I'm gonna get the exact same answer. So if I do it once for this curve, I know what the answer is going to be everywhere along this curve, right? And then we said, well, if I change function, depending on the function type, I'm gonna get an answer, and that answer is always gonna be the same. So if I just recognize and I find the pattern, I don't have to go through this whole process and just figure out what that pattern is. And the pattern is summarized by those rules. Okay, just so that we don't have to go through all of that. Okay, but going from here to here is equivalent to having done this whole lengthy problem with the h. Yeah? Questions? Is all good? What about this one? What is the slope of that guy? So this is a considerable leap from the problems we did before to this. They require several steps. What is the first step you would use? If you're taking Cal 2, just,
Okay.
or higher, just quiet.
I will.
So, to me, this is complicated, right? So the easiest thing would be kind of break it down into more accessible problems. I will use this property right here just to break it. So I use number 3, and this becomes the derivative of 2x squared minus the derivative of 1, or I should say plus derivative of minus 1. That's this part right here. That's more logical to do it this way. So I need to worry about the first part. This is a number that multiplies a function, isn't it? So if it's a number, there is a number in front of the function, what do? You use property number 4. Property number 4 says that you can just take the number here and multiply that times the derivative. So this is property number 4. Now here, this is just a constant, so the derivative of a constant is by property number 1
0.
is 0. So I get that. So now I have a 2, and now the derivative of a power. So the derivative of a power is property number 2. So this is 2 times, what is the derivative of x squared? It's number, exponent becomes the coefficient, and then x exponent reduced by 1. So you get 2 times 2 is 4, x. Yeah? Questions? So how many of you want to murder me right now? Only one, that's okay, I can handle it. I can run faster, I think, maybe.
Probably.
Downhill.
Yeah, you can.
So, anybody else willing to kind of kill me right now? So what are the important things here?
Remember the rules?
So before that, what are we doing?
For finding the slope of a function.
So we are concerned with figuring out a fast way to evaluate the slope along a function, right? If you remember last time we said it's because eventually we're going to use that to find the max and the min of a function. So we have an objective in mind, but it's kind of far away down the road. So what is the one way that we learn how to find the slope? We say, well, pick 2 points, calculate the slope. Now, if I want to calculate the slope of a point instead of 2 points, I just need to pick 2 points that are very, very close to each other, right? So far it's good? All right. But what have you realized in doing all of that? Well, it's a real pain to do. So is there a shortcut? Well, the shortcut is have mathematicians play with all possible functions and come up with slopes, and eventually find the pattern that can allow you to skip all this work when you're trying to compute that slope. The pattern is summarized by those rules. So if you have a particular function that happens to be a constant, the slope of it is a constant, is 0, sorry. If you have a function that is some type of exponential, then the slope can be calculated by doing this. How do they go from the question, find the slope of x to the n, to the slope is this? The way they did it, they used this approach. Took them an hour, 2 hours, whatever. And then eventually, what about if you have a combination of functions? How do you handle it? Well, you do this. You take the derivative of the first function, and then you add the derivative of the second. How do they know that? Well, they pick a combination of functions, they did all of these, and eventually, hours later, they arrived to that conclusion. So, this is just a way to compute the slope without having to go through this whole painful process. Does it make sense? So this is the idea that we're trying to do. Now the mechanics of it. Well, once you memorize the rules, if I give you a problem, it's not gonna be that bad. We're gonna do a few of them. You're gonna do quite a few of them on D2L. But then eventually we're going to do the problems of maximum minimum. Okay, so let's do a couple more of those guys, and then we'll move on to maximization. Is it better?
Yeah,
No murder anymore, just like hurt.
Well, I'm understanding how to find the slope because I've known that since like 8th grade. But it's just the derivative parts that's tripping me up, I think.
So do you understand what that represents though?
It's representing you said something about the equation.
So it represents a formula. So when I do this is a formula that tells you what the slope along this thing is.
Right, okay.
Okay, so that's what that derivative represents. It represents, if I want to know the slope of this function when x is 3, or pick another number, sorry, 5, all I need to do is put a 5 here. Calculate the total, and that tells me what the slope is.
So the derivative is the slope of the curve.
The derivative is a function that represents the slope or anywhere along the curve.
Okay,
Yep,
got it.
good. Did I say it correctly? Yep. Any questions?
So like for that one, for that derivative, x to the power of 4, so that's a rational function, and
Hold on. Which one?
the first example.
This one.
So that's a rational function for a parabola, and so whenever you calculate through it based off the rule, all you gotta do is plug x in for whatever point you want to find. for the
That's
slope.
right. Yeah. So I'm gonna do an example like those. So we'll replicate that without going through all that process. So let's try it. Let's find the slope of this thing when x is 3. What is the answer? We calculated before, the answer was 6, right? So let's try to do the same thing. I'm gonna do it all the way there. Find the slope.
Fall asleep, are you? No.
X squared.
Struggling. That's what's happening. Yeah. I haven't done this crap in years. I haven't done it for very long. It's just taking the process a little bit
So
longer.
the proper way, the way we did it earlier was by pick a point next to it, calculate the slope, then take the limit to make those 2 points adjacent.
Do you want this in the? Yeah, sure.
But now we know derivatives, so compute the derivative of x squared. So what do you get? It's the power rule, so you have exponent. Exponent becomes the coefficient x, the new exponent is 1 unit less than the old exponent. So you get 2x. So if I want to know the slope anywhere along x squared at any point, all I need to do is pick the location where I want to compute the slope and plug it for that. In this particular example, I want to compute the slope at x equal 3. So all I need to do is take the derivative that I already computed and evaluate that at x equal 3. So what is the derivative? We said the derivative is this guy, 2x, evaluate that at x equal 3. 2 times 3 is 6. Yep. What if I wanted to compute the derivative at x equal 10? What would change?
You would plug in 10 where the x is.
Just plug in 10 in here?
Yeah.
And what is the answer in that case? 2 times 10 is
20.
20. So all I need to do is just change the value where I'm computing the derivative. Yep. Questions? What if I give you, what is the slope? Oh. These at x equals 1. So again, you have two options. The first one is, this is your first point, pick a point next to it, then evaluate this function at x equal 1, then evaluate this function at 1 plus a bit, then compute the actual slope, and you got the answer. The alternative is take the derivative. So, the derivative of 3x squared minus 4 is, so we need to simplify this thing. So split it, the derivative of 3x squared plus the derivative of minus 4. Yeah, what property did I use?
The second rule.
Is the one that allows me to split stuff, which is rule number 3. Yeah. So now I need to worry about the first part. This is a constant times x times a function, so I need to pull the constant in front of the derivative. And then the derivative of a constant is 0. Alright, so now I have 3 times the derivative of x squared is
2x.
so it's x to the power, so I take the exponent, x to the exponent reduced by 1. And I get 6x. Okay, so regardless of what point I'm considering, if I want to calculate the slope, that will be it. Now the specific point, since I'm interested in x equal 1, then we have taken the derivative of the original function. Which happened to be 6x. And then I need to evaluate that at x equal 1. So it's 6 times 1. 6. Yep. Questions? So what is your responsibility? In the exam, I'm not gonna give you a problem where you have to calculate derivatives. I think as a graduate in a degree in finance, you need to know what a derivative is, have an idea of it, know what the concept is, and you will have to take some derivatives for the quiz. So you're gonna do it open notes, you can both together. I want you to just practice. This is not very difficult stuff at the end. It looks intimidating because we did it really fast, but the general idea and the mechanics of it is doable. There is one more step, which is the reason why we're doing all this crap. The next step is to actually be able to identify what a function is its highest value or its minimum value. So I want you to be able to do that. What I will ask you in the exam, most likely, is the process. So if you have a function and you want to find the maximum, how would you do it? And you will tell me, well, you take the derivative, you will see that then you have to set it equal to 0, and then you solve. It's a 3-step algorithm. That's what I want you to remember. Throughout the semester, I will be using this stuff. I will do it in class. So if I'm deriving a formula because I want you to understand how everything works, I will do the derivative for you in class. I will not expect you to derive formulas for the course. That's not your responsibility to derive them. Your responsibility is to get an idea where this stuff comes from and use it. That's it. So that's pretty much where we're going. I want to give you the tools to understand what's going on, so that if you have a conversation with somebody that knows this stuff, you can follow and you can contribute. If they ask you how to compute the derivative of cotangent, I say, I don't know, but I mean, I can look it up. But you know what that means in general, even though it's a function that you don't know what it is. That's pretty much what we need to add. Okay. Questions? Do you feel better? Okay. So, do you want me to do more examples, or do you think we can move forward?
Should we do one more example?
One more example? I mean, this is by far the most difficult function that you will encounter.
Oh, no, we're good.
So, we can do one more.
I don't mind. I mean, what if you threw a curveball on
Oh, that's a curveball over there.
I mean, he said this is the hardest, so I'm expecting
It's
this
among
to
the
be
hardest.
easy.
I can do one more complicated, but you'll see that there is not much more to it. What is the no, I don't like numbers. Let me pick some. I always do the same shitty numbers. I don't know why. My imagination is so- all right. That. So can you guide me through the process? What do we need to do first?
Split it up.
Split it up.
So take the derivative, right?
Mhm.
That's step one. So take the derivative of this guy. And eventually evaluate that derivative for a value of x equal to 2. Yep? So derivative of 5x to the 4th plus 3x squared minus 10. So now how do you evaluate the derivative? You will apply the rule number 3 and split all those terms. So break it down into simpler problems. Derivative of 5x to the 4th, derivative of 3x squared, derivative of minus 10. Do you agree with that? So use the rule to decompose this thing. So now we worry about one term at a time. This is the same as 5 times a function, so you can write this as 5 times the derivative of x to the 4th. This one is 3 times a function, 3 times derivative of What about the last term?
Zero.
Zero.
Equals zero.
Why?
This
Because
is the constant.
It's the derivative of a constant, right? And so what is the slope of a constant?
zero.
It's
Yeah.
zero, so its derivative is zero. Good. Alright, cool. Next step. Derivative of x to the fourth, so power rule. What do you do? It's 5 times. What do you do here? You take the exponent, you write it in front of the x, and then you take the old exponent and reduce it by 1. Yep. Then you have 3 that multiplies, same thing, power rule. The coefficient is 2, x to the 2 minus 1. So what do you get?
20x to.
This is 20. And then x to the 4 minus 1 is 3. 3 times 2 is 6. And just x. Yep.
Mhm.
Questions? Are we done? You sure?
Yeah, good, like, we did it, x.
The original question was, tell me the slope at a specific point. This is the equation of the slope anywhere, right? So since we're looking at the slope at x equal 2, so this is equation of slope in general. But I need to evaluate that at x equals 2. So you get 20, 2 cubed plus 6 times 2. 8 times 20 is 160, 172. Is that right? Questions? You good? I cannot think of anything more difficult than that. So I can give you higher exponents, more terms, but pretty much the algorithm is gonna be the exact same. Okay, and the one I'm gonna do, and I'll be doing that, not you, is the derivative of a rational function, which is complicated. But there is no sense to teach it, just do it once, and so that's what I wanna stop. So when it's time for me to do that, trust me that I'm doing it right, and then verify the answer with the textbook to make sure I didn't mess it up. But I want you to have the general idea. So you will understand what I'm doing, for sure. Questions? So let's try to use this thing. Slope at the maximum or minimum of a function. So let's see what happens when a function is reaching its highest point or its lowest point. Scenario. So let's suppose that is a function of it. And what is going to happen to the slope as we move along this thing? What is the slope? Positive or negative?
Positive.
It's positive and pretty high, right?
Yeah.
But as I move forward, what is happening to the slope? It's getting progressively smaller.
So
What about here? What is the slope on this side?
it's gonna go
Negative.
down negative.
So what happens is that as here you have, in this general region, you have high positive slope. But then once you pass this point, you have progressively higher negative slopes. Well, what must happen when you go continuously from positive numbers to negative numbers? You will pass through zero.
Zero.
In fact, if you look at the highest point is characterized by the highest point has a slope of zero. Yeah? What about the lowest point? Well, suppose you have a function does weird stuff, then does something like this. On the left, at the minimum, what is the slope? It's negative. And so on this side you have negative slope. But then what about here? The slope is positive. So what happens at the bottom? Well, you're going to transition from negative slopes to positive slopes. So in that transition, at some point, you will have zero slope. Turns out that the bottom, lowest point, the slope is zero. So we want to exploit that. And so without knowing anything, just by knowing these, let's go back to the problem before. And is the slope of this thing, I mean, is this, at x equals 2, does this function have its maximum or minimum? How do you know? Well, when we calculate the slope, what do we get? Some number that is not zero. So that means that at x equal 2, this function is not reaching its maximum or minimum. It's either fast or has yet to arrive. We don't know. We just know that it's not the maximum. Okay? What about what was it? This guy. This is the function, x squared. If you actually plot it, how does x squared look like? If you plot it accurately. It's a parabola, right? And where does it sit?
Zero.
In the origin? Shit, I always guess what. So. And Italy is the land of artists and poets, and neither one. So, what is the maximum min?
The min is 0.
So the maximum is gonna be somewhere here and somewhere there, right? But what about the minimum? Is that x equals 0? Is it true? So if you take the derivative we computed for this guy, this was the derivative. If you put 0 for x, what do you get?
Zero.
So that tells you that we don't know how to do it formally, but we know that if you check at x equals 0, you get a derivative 0, meaning that you have either a maximum or a minimum. Okay. So mathematically, it appears to be supported. So can we come up with an algorithm that allows us to find whether a function has where a function has a max or a min? How would you do it? So if I give you this weird function, we don't know what the formula for it is. It's that weird. How can you tell me if this is a max or min? There is only one thing that you know. If it's max or min, the slope is 0. So how would you find the point where the slope is 0?
Find the inflection point.
So just shush. So let's arrive to it. We know that the maximum is where the slope is 0. how about we take the derivative of this function, come up with a formula. So we take the derivative, we come up with, say, this thing. And then we say, all right, if I plug numbers in here, eventually I might get lucky and find a number where the slope is 0. If I find where the slope is 0, then I found the location of the max or min. Alternatively, I can just say, hey, I want to force this to be equal to 0. So you set it equal to 0, and then you solve for x. By doing that, you find the value of x that makes the derivative equal to 0. Implicitly, you found the location of the max or the min. So let's try it out. Finding, what's that I have?
13.
Yeah.
Finding the max or the min of a function. So, step 1, compute the derivative of that function. Okay? So do whatever we've done up to now. Then step 2, set the equation obtained from step 1 equal to 0. So in other words, whatever you got, make it equal to 0. Then step 3. So the equation from step 2. Right. And by doing this gives you the value. This tells you the x value for which f of x as a max by min. Yeah. So let's try one really fast. Let's do, hold on, I did it in my head first. Find the location where f of x equals x squared minus 2x plus 1 as its max or min. Okay, so I want to figure out where that function reaches its highest point or its lowest point. I don't know how it's traced. And this approach will find either one. So what is the algorithm? So step 1, compute the derivative, x squared minus 2x plus 1. So now we need to worry about that. Once you find an answer for that, what is the next step? We take that outcome, we put an equal sign and 0 next to it, and then we do some algebra to solve. So let's see. We need to decompose this thing, the derivative of x squared plus the derivative of minus 2x plus the derivative of plus 1. Do you agree with that? So what is the next thing? Exponent power rule. And so this, you take 2 becomes the coefficient, x, the 2 minus 1. Then this one is the constant derivative of just x, and then it's 0. And with that, I just only did one little step there. So the first part becomes just 2 to the x. And then here you have minus 2. What is the derivative of just x? The x is what? X to the 1 power? So if you apply the power rule, what do you get?
1.
Is 1 times x to the 1 minus 1, because this is x to the 1. What is any number to the 0 power? 1. So this is 2x minus, this is 1. 2. So this is the equation of the slope. So now we do step 2. Set 2x minus 2 equal to 0. And then solve 2x minus 2 for x. So I have 2 to both sides, then divided by 2, x is 1. Yep. So now I can even graph this thing. And if x is 1, this thing will have its minimum. Now, I'm not gonna graph it accurately, but you can get an idea. This thing is gonna be like that. The minimum occurs at 1. I don't know where the minimum is at, you know, how high it is. I don't even know if it's a max or a min. I just know that it is, well, I know it's a minimum because of the way the function looks like, but I just know that the function is either like this or it could be like that. And I know that the highest or lowest point occurs along this point. If I want to know the exact location of the max or min, then I would have to take this number, plug it into the original equation, and that will tell me the location of the max or min. We're going to do that next time. So what do you need to remember for today? What is the concept of derivative? What is the derivative computing for you?
The slope at any point.
Gives you the equation of the slope along the function, right? It's an efficient way of doing that instead of doing things point by point. And they developed a bunch of different rules for derivatives. There is probably about 100 by the time you take count 3. And some of them apply to trigonometric functions and weird stuff. But the ones that we care about are only those 4. So if you want to figure out the slope of a function at some point, what do? You just take the derivative and then evaluate the derivative at whatever point you're interested in. Then from that we said, all right, we know how to handle it. Why are we doing all this stuff? Well, there is this observation that if a function reaches its highest point or its lowest point, the slope of the tangent line at the max or the min is 0. So we're going to exploit that to kind of work things backwards and use the derivative to find where the highest point or the lowest point of the function is. Okay? And so this is the algorithm that allows you to do it. So that's the general idea, and this is an application. So on Monday we're going to do some more applications of these, and then you can play with the quizzes in D12 and just do this stuff on your own. And then we start the actual semester. But you probably did about 2 months of calculus a day and a half. So if there is some confusion, it's normal. And but just don't panic, I mean, just focus on understanding the area. The more concerned that you understand the area, then you actually know. I mean, that's pretty much the way it is. If you don't have any questions, I'll see you on Monday.